So supercritical fluid chromatographic technique is a separation technique which is used for the isolation or separation and quantification of the solutes by using the stationary phase, which will be commonly employed in either gas chromatography or liquid chromatography, and the mobile phase of a supercritical fluid. The mobile phase used in supercritical fluid chromatography is a supercritical fluid because of the varied properties such as density, viscosity, and diffusion coefficient of the supercritical fluids. The supercritical fluids are more popularly become to be used as mobile phases for the separation of variety of the compounds. So in today's class, let us discuss about the background of this supercritical fluid chromatography and instrumental aspects such as injectors, column, mobile and stationary phases, detectors, especially used in chromatograph, supercritical fluid chromatograph. Let us discuss one by one. And what are the advantages of supercritical fluid chromatographic technique? And what are the disadvantages? How can we compare the performance characteristics of supercritical fluid chromatography with HPLC and GC? And what are the relevant applications of supercritical fluid chromatography? Let us discuss one by one. So as I define the supercritical fluid, the temperature pressure phase diagram is presented here. So you are very familiar about the supercritical fluid now. Supercritical fluid is going to be formed whenever a substance is heated above its critical temperature and the pressure is adjusted to above its critical point. So the density, viscosity, and the diffusion coefficient of these supercritical fluids will make the substances to effuse through solids like a gas, and the supercritical fluids property will make the substances to dissolve just like a dissolution in liquid. And the kinetic energy and intermolecular forces will be distinguishable when you compare the kinetic energy by the virtue of motion of the molecules in supercritical fluids with the intermolecular forces of other substances. So therefore, supercritical fluids are highly advantageous. And if you look at the properties and the statistics with respect to density, diffusion coefficient, and viscosity of supercritical fluids, these values I have presented before also. Supercritical fluids will be having higher density when compared to gaseous substances, and even when compared to liquid substances, the density will become always advantageous. And the diffusion coefficient of supercritical fluid will be greater than liquids. Therefore, the diffusion of the solute into the supercritical fluid will be more prominent and comfortable. Therefore, effusion or diffusion of the solute molecule into the supercritical fluid will become highly excellent. And one more parameter is viscosity. When you look at the viscosity of supercritical fluids, the viscosity is lesser when compared to liquids, and therefore the lower viscosity of the supercritical fluids is an added advantage, especially in performing the separation process by using supercritical fluid as a mobile phase. So with these varied properties, in the year 1982, a famous analytical chemist known as Hewlett Packard, who has contributed his work for the development of supercritical fluid chromatographic technique, especially in the 19th century. So, who proposed the use of supercritical carbon dioxide for the separation of variety of the compounds by utilizing the principle drawn from either gas chromatography or high performance liquid chromatography. So the principle of separation remains the same in supercritical fluid chromatography also, and this is resembling with respect to the principle when compared to gas chromatographic technique. But in gas chromatography, gaseous mobile phase is going to be used, but in supercritical fluid chromatography, the mobile phase is going to be supercritical fluid. And even the principle can be comparable with high performance liquid chromatography, where the liquid mobile phase can be used, but here the supercritical fluid can be used as a mobile phase. So what kind of compounds can be separated by this supercritical fluid chromatography? So almost all variety of the compounds which are excluded from the separation by GC and HPLC can be subjected for separation by supercritical fluid chromatography. Especially highly polar components can be easily separated, and the compounds which are having large molecular weights can also be separated. And here the principle involved in the separation of large molecular weight compounds will be adopting, especially from the size exclusion chromatographic technique, because the size exclusion chromatographic technique is also used to separate the molecules based on the molecular masses. And it is highly impossible to separate the non-volatile and thermally labile compounds from GC, because in GC the temperature will be raised at least to 400 to 500 degrees Celsius. The compound should be volatile. It must be able to convert it into gaseous form or vapor state. Therefore, if such molecules, it is impossible to convert them into vapor state, then those type of compounds cannot be subjected for separation by GC. But here, all those non-volatile and thermally labile compounds can be subjected for separation, because the temperature we are going to maintain during the separation process in supercritical fluid chromatography will be ambient to say 40-45 degrees Celsius. If we use the supercritical fluids such as ammonia and butane, temperature may be raised to more than 100 degrees Celsius. In such cases, we have to look after the compounds whether they are thermally labile or thermally stable. If they are thermally labile at the temperature above 100 degrees Celsius, those supercritical fluids are not suitable to be used as mobile phase. So we have to search for other alternate mobile phases which can exhibit the supercritical fluid property at that particular temperature. Then only we can go for separation. And all those compounds which are undetectable by HPLC detector can also be subjected for separation by supercritical fluid chromatography. Here, supercritical fluid chromatographic column will be having the stationary phase as same as either gas chromatographic or HPLC column, but only difference is in the mobile phase. In supercritical fluid chromatography, the mobile phase used will be supercritical fluid. So commonly we will be using in HPLC absorption detectors or refractive index detectors or fluorescent detectors and other detectors. When those compounds are unable to be detected by such detectors, here a special designation or special arrangement will be made in order to detect the compounds in such a way that no compound can be excluded from the operation. So supercritical fluid chromatography technique is designed in such a way that all those compounds which are excluded from the separation employing gas chromatography and high performance liquid chromatography technique can be easily subjected for separation by supercritical fluid chromatography. Here you can see the instrumental aspect, the schematic of the instrument which will be used for the separation of the compounds in supercritical fluid chromatography. As you saw yesterday, while explaining the instrument for the supercritical fluid extractor, here the supercritical fluid containing tank is required, and supercritical fluid will be acting like a mobile phase here. That is going to be mobile phase. And more commonly assume if supercritical carbon dioxide is employed as a mobile phase, carbon dioxide will be present in this tank, and this is connected to a pump because we need to create a pressure, and at the adjusted pressure we need to bring the pressure above its critical pressure so that the carbon dioxide can be converted into supercritical fluid. And the mobile phase from the carrier tank will be passing through the pump. At the adjusted pressure it will be moving towards the chromatography column. The column is placed inside the oven because temperature is a matter here. So the sample is injected in the injection port or in the injection system, where the sample will be introduced either in the liquid state or in the solid state, whatever it is, either in the liquid or a solid state. So soon after the introduction of the sample in the injection system, that will be carried by the supercritical fluid towards the column, where the column is containing. You can see the movement of arrows here, how the separation process is going to be taken place. The solute molecules are going to be circulated in this circulated coil. A coil-like column is used here, and the column used in this supercritical fluid chromatography may be open tubular column or packed column, whatever it is. In GC, we will be using two types of columns, open tubular columns and packed columns. Open tubular columns are made by silica coated by polyamide compound at the outside, and that brownish color is imparted due to the polyamide coating. And the same column can also be used in supercritical fluid chromatography. whenever the low sample throughput is required. If the sample throughput is very high, we can use packed columns which are made by stainless steel or glass, whatever it is. So this is the cross-sectional view of the column. You can see here, cross-sectional view of the column. The packing material is present. If it is an open tubular column, there will be no packing material. The starting material used to construct the column itself will be acting like a stationary phase. So the solute molecules, dependent upon their polarity or dependent upon their relative affinity towards the column, they are eluted one by one. They are eluted one by one. Once the separation is over, all those solutes getting separated will be reaching towards the detector, and the detector will be giving the signal with respect to the analyte, whatever present in the sample, and at the end we will be ending up with a chromatogram. So this chromatogram will be used just like use of chromatograms obtained from gas chromatography or high performance liquid chromatography, so that they can be utilized in order to identify the species and in order to quantify the species present in the sample. So this is about the schematic of supercritical fluid chromatograph. The supercritical fluid containing tank will be present because this is going to be employed as a mobile phase. And here pressure regulator and the regulator, everything will be fixed here in order to release the gas. There will be a valve, and by means of the valve, by rotating the valve, supercritical fluid can be released towards the pump. Pump is used to adjust the pressure because pressure adjustment is very, very important here. And the sample is introduced from the injection system. This is going to be the head of the chromatographic column. The injection port and the column is placed at the oven. So the oven containing the column is having the packing material, and this packing material is going to be functioning effectively during the separation process. So as a result of the relative affinity of the solute molecules towards the stationary phase present in the chromatographic column, the solutes are going to be separated one by one, and the separated solutes, separated components will be reaching the detector ultimately. Thereby, the detector will be giving the signal by amplifying the property of the solute molecules, and at the end, you will be getting a chromatogram. So this chromatogram can be employed for your usual purpose. So this is about the schematic. And here another schematic diagram. This is a cross-sectional view of supercritical fluid chromatograph, where also you can see a tank containing supercritical carbon dioxide. And here there is a special arrangement has been made, and it has been connected to a mixing chamber followed by a pump. Pump is connected to the supercritical carbon dioxide because pressure is needed to be adjusted to the carbon dioxide in order to attain the supercritical fluid state. You can see methanol here. As I told yesterday, methanol can be used as an organic modifier in order to regulate the polarity of the mobile phase. So supercritical carbon dioxide is non-polar because it do not possess any dipole moment. It is a linear molecule, and hence it is a non-polar molecule, and it is not suitable for the separation of polar solutes. Whenever the polar solutes are present, we need to modify the polarity of the carbon dioxide, and that will be done by simply mixing the mobile phase with modifiers such as methanol, propylene carbonate, and hydroxyethanol, etc. So these organic modifiers are also supplied by means of the pump at the adjusted flow rate, and the organic modifier in the supercritical fluid as a substance will be moving towards the mixing chamber. Here, the mixing up of supercritical substance and the organic modifier takes place. After mixing, under the regulated polarity, this mobile phase will be moving towards the chromatographic column. Before the chromatographic column, there is a injection port, and through which the sample is going to be injected. So the mobile phase as a supercritical fluid in the presence of the organic modifier will carry the sample whatever injected into the chromatographic column, in which the separation is going to be taken place. Then the separated solutes will reach the detector. Then at the end you will get a chromatogram. No need to explain more on this because already we have explained in the gas chromatography, HPLC, ion exchange chromatography, size exclusion chromatography, and affinity chromatography, etc. So on all the things, all other things except the solutes, even including the solutes, they will be going as a waste. If you require this waste for further investigation, you can collect this. Otherwise, you can drain this. So this is the cross-sectional view of supercritical fluid chromatograph. So By using these type of instruments, the injection volumes of greater than 96 nanoliters can be introduced into the chromatographic column in order to perform the separation process by supercritical fluid chromatography. If you introduce more volumes, if it is greater than 96 nanoliters or greater than 500 nanoliters while using open tubular columns, this is going to affect the resolution, because if the sample is overloaded into the chromatographic column, due to overloading of the chromatographic column, fronting is going to be the effect. So fronting, definitely it is going to impair the resolution. As a result of the impairment of the resolution during the chromatographic separation, that will definitely increase the band broadening, and as a result, the height of the theoretical plate is going to be increased. So we must be very careful about the volume of the sample solution, what is needed to be introduced into the chromatographic column while using the open tubular columns. So at least greater than 96 nanoliter is recommended while using open tubular columns. If you use packed columns, greater than 1 microliter can be introduced, and packed columns are employed especially whenever if we are needed to introduce more volume of the sample. So open tubular columns are more commonly used in supercritical fluid chromatography rather than packed columns. So it is highly advantageous. Packed columns are less efficient. You will be getting less number of theoretical plates in packed columns. And this is also used in HPLC also and even GC also. So whenever the sample throughput is more, we have to use packed columns. Whenever lower sample size is needed to be introduced, we will be using open tubular columns. And the solvent delivery system will be playing a very important role, especially the flow rate. Flow rate, at what flow rate the solvent is traveling through the chromatographic column. So at least 1 to 10 microliter per minute must be maintained while using open tubular columns, or 1 to 10 ml per minute while using packed columns, because the internal diameter of the open tubular column will be very, very less when compared to the internal diameter of the packed column. Say for example, zero point 0.1 to zero point 0.5 millimeter will be the internal diameter for open tubular columns, whereas the internal diameter of the packed column will be zero point 0.5 centimeter at least. Therefore, the flow rate must be minimized to 10 microliter per minute in case of open tubular columns, but in case of packed columns, the flow rate will be maintained up to 10 ml per minute. So the pressure is maintained at 60 megapascals. 60 megapascals will be the appropriate pressure we need it to be maintained. And the mobile phase, because it is mixed with the organic modifier under the liquid state, under the applied pressure, that will be moving towards the chromatographic column. So no need to explain more about the movement of the mobile phase here, because mobile phase before reaching the column, it will be in the liquid state, because liquid methanol has been mixed with the carbon dioxide. Once the mobile phase about to reach the chromatographic column, then only it will be converted into supercritical fluid. And as far as injectors are concerned, all those injectors, especially an hypodermic micro syringe, which is used to introduce the sample into the head of the chromatographic column, either in GC or HPLC, and all those injectors are used even in supercritical fluid chromatography also. Even splitters, and without using splitters, we will be introducing the sample, because the advantage of using a splitter is in order to avoid the overloading of the sample to the chromatographic column. Whatever the adequate size of the sample is required to be introduced, that much amount of the sample will only be introduced into the chromatographic column, and the rest of the sample will be going as a waste. So that's what the splitters or splitless injection system will be done, especially for open tubular columns. And around 0.01 to 0.05 microliter injection will be made while using open tubular columns using split injectors, and 0.01 to 0.05 microliter injection of the sample will be done while using splitless or splitter injection system. So you must remember about this. Splitters are used to introduce the required size of the sample into the chromatographic column. The excess sample, whatever introduced, that will be going as a waste. And the columns, what we will use in supercritical fluid chromatography, mostly they are resembling with either GC or HPLC. If you consider open tubular columns, which can be derived from GC, because of the advantages of producing the large number of theoretical plates. At least you can see here, almost 500 times greater number of theoretical plates are anticipated while using open tubular columns of gas chromatography technique. And another advantage of using these open tubular columns is it is easy to control the pressure drop. The pressure drop will be very low while using the open tubular column because there will be no packing materials inside the chromatographic column. As a result or as a consequence of the absence of the packing material in the chromatographic column, the eddy diffusion term or multiple path transfer term of the band inter-equation will become zero, will be absent. Therefore, the band broadening will be minimum, the height of the theoretical plate will also become minimum, and hence, as a consequence of the low height of the theoretical plate, the column efficiency will become very high. Therefore, I have presented here the number of theoretical plates while using open tubular columns of gas chromatography for supercritical fluid chromatographic separation will be at least 500 times greater. And even packed columns made by stainless steel or glass, which are used in HPLC, can also be used in SFC because of faster analysis and able to be maintained with a higher flow rates. And whenever high sample is needed to be introduced into the chromatography column, these packed columns are also advantageous. So the open tubular columns which are used in supercritical fluid chromatography are somewhat smaller when compared to GC capillary columns. The dimension will be typically 10 to 20 meter in length and 50 micrometer internal diameter. The dimension of supercritical fluid chromatography column will be 10 to 20 meter in length and 50 micrometer internal diameter. As a result of this very low internal diameter of supercritical fluid chromatographic columns, the height of a theoretical plate will become minimum. This is the advantage. And the mobile phase must be more stable due to extreme conditions of supercritical fluids. You must remember about this. The mobile phase must attain the stability because of the conditions what we are going to regulate during the separation process. We will be raising the pressure, we will be raising the temperature in order to attain the supercritical fluid state. While doing so, the composition of the mobile phase should not be changed, it should be intact. So as a result of these advantages, the columns will be adding highly excellent results while performing the separation in supercritical fluid chromatography technique. And packed columns, as I told you, which are very similar to HPLC columns and which will be having 10 or 5 or 3 micrometer porous particles at stationary phase. They are homogeneously and consistently packed into the packed columns. Whether the silica-based stationary phase can be used or modified silica materials can be used as stationary phase. And the column dimension will be 10 by 4.6, 10 centimeter length and 4.6 millimeter internal diameter will be the dimension of the column. So, as I told you, the lower viscosity of the supercritical fluid is an added advantage in order to perform the separation in supercritical fluid chromatography. And how this is going to enhance the separation scientist in utilizing these columns or in utilizing these mobile phases. Say, for example, because of the lower viscosity of the supercritical fluids in supercritical fluid chromatography, whatever the length of the chromatographic column you are required to perform the separation, you can use it. There is no any problem of band broadening. There is no any question of reduction in the efficiency of the separation. So as long as the column you wish, you can use it. So longer than liquid chromatography column can be employed in supercritical fluid chromatography separation. Especially in open tubular columns, 10 to 20 centimeter will be the length, which is going to have the internal diameter of 50 to 100 micrometer. So, and this is same as fused silica open tubular columns, so what we can use in gas chromatography. Fused silica open tubular columns are made by fused silica. Silica itself going to function as a stationary phase there. And silica is highly polar, and the polar interaction is going to be expected there. And unwanted adsorption needed to be destroyed. In order to do this, we may have to modify the silica by bonding or chemical treatment. So you have understood the principle of supercritical fluid chromatography now. You have to remember these 3 points here. Smaller the column diameter, the efficiency will be very high because the pressure drop will be very low if the column diameter is very low. Especially while using open tubular columns, the separation will become highly efficient because of the zero value of the eddy diffusion term. If the density of the supercritical fluid is increased, the efficiency is going to be decreased because we may have to increase the pressure in order to make the movement of the supercritical fluid comfortably through the chromatographic column. So the supercritical fluid with higher density, it is definitely going to decrease the efficiency of the separation. So therefore, you interest to decrease the column diameter, therefore the column efficiency can be increased. And while playing with the temperature, you must be very careful about what temperature you have adjusted, whether the substance has attained the supercritical fluid state or not. And you have to concentrate on diffusion, solubility, and volatility while playing with temperature. And as a result of the minimal pressure drop while using the open tubular column, you can look at this equation H is equal to diffusion coefficient of the solute in the mobile phase and the linear velocity of the mobile phase. Everything is associated here, and this is in the form of B by U plus CS into U plus CM into U. This is the modernized version of Van Dimter equation. Modernized version of Van Dimter equation. Here, the first term is absent, that is a diffusion term or multiple part transfer term is absent because we are using open tubular column where we are not going to use any packing material. Open tubular column containing the silica. Silica itself going to play a stationary phase role. Therefore, the multiple part transfer term and the eddy diffusion term is absent here. And this is the longitudinal diffusion term, and this is going to be the mass transfer term in the stationary phase, and this is the mass transfer term in the mobile phase. So the value of H is going to be decreased as the value of U is going to be decreased, and similarly, the diffusion coefficient of the solute into the mobile phase is decreased. And here, the reciprocal of the linear velocity of the mobile phase is also going to affect the value of H, as you can see by means of this particular equation. So now you better understood about the advantages of open tubular columns. Open tubular columns which are having lower internal diameter, and hence the first term of the Van Dimter equation will become zero, will become absent. Therefore, the column efficiency will be very, very high. You can see here how the height of the theoretical plate is relied upon the terms dm, dm, and ds in the Van Dimter equation. And similarly, you can see the packed columns. Packed columns will be having 10 to 25 centimeter length, and the number of theoretical plates we can achieve will be 1 lakh. Will be 1 lakh. So the packing material, what we will use as a stationary phase, that will reduces the permeability and creates flow resistance to the solutes if the length is less than 25 centimeter. So here, if the density is increased, the diffusion coefficient of the solute in the mobile phase will decrease. Therefore, the efficiency will increase. So you can expect only increased efficiency by increasing the density while using packed columns. And you have to concentrate on the multiple part transfer term in Van Dimter equation, how to reduce the value of H whenever the solute is moving in multiple parts. That is only by decreasing the particle size. If the particle diameter is very low, that can be consistently packed into the chromatographic column. And as a result of the lower particle size, the value of the H will also become low. So as the value of H become low, the N value will become high, and therefore the efficiency of the separation will become high. Column efficiency will become very high. And as a result of this lower particle size, the pressure drop will also become lower. Therefore, these are the common factors you must remember always while using the packing material or while using the different columns or variety of the columns in order to perform the separation. So, and one disadvantage while using silica-based stationary phases is the adsorption, physical adsorption. Physical adsorption leads to increased band broadening. Therefore, the column efficiency is definitely going to be suppressed while using silica. So chemically modified silica particles can be used which are having thickness from 0.05 to 0.4 micrometer are always employed in order to decrease the particle size or in order to decrease the physical adsorption, thereby the column efficiency can be increased. So you can see here how the retention time in supercritical fluid chromatography is related to the mobile phase linear velocity. So the retention time of the solute after which the solute is going to be eluted from the chromatographic column is inversely proportional to the linear velocity of the mobile phase. So L by U, where L is the length of the column, K is the retention factor or capacity factor of the solute, and that decides the average migration of the solute or relative migration of the solute in the chromatographic column. According to this equation, packed columns are more efficient with higher density analytes, and open tubular columns are more efficient with low density mobile phase. So if the density is increased, the column efficiency is going to be decreased. The retention time will become longer. The retention time will become longer for the low density analytes, and the retention time will become lower whenever the solute moving through the chromatographic column is having higher density. This table summarizes the efficiency and the dimensions of the columns what we will use in supercritical fluid chromatographic technique. So the internal diameter and length are presented here. If you use conventional packed column, the ID will be 2 to 4.6 millimeter, and which will be having a length of 0.03 to 0.25 meter. Similarly, microboard column can also be used. Packed capillary columns can be used. Open tubular column can be used. Open tubular columns are having lower internal diameter, and the length can be increased up to 35 meter. So TR is equal to L by U. Even if you increase the length of the column, we can increase the retention time of the solute. Thereby, the resolution can be increased. Thereby, the co-elution of the pair of the solutes can be avoided. The solutes can be eluted one by one. This is the advantage of increasing the length of the column. So in packed capillary columns, lower volumetric flow rate can be expected. So more compatible with mass flow detector can be expected while using packed columns. And the sensitivity will become very high when you use the detector which is more compatible to measure the property of the solute. So as a whole, we can sum up that the packed columns are also advantageous whenever a suitable detector is available in order to get the signal for the solute with respect to its amount present there. So here, now you have better understood about the principle of supercritical fluid chromatography, the length of the column, the dimension of the column, and the type of the column what we can use in supercritical fluid chromatography will decide the efficiency of the separation. So the efficiency of the separation is not only dependent upon the solute characteristic, but also it is dependent upon the column characteristic and the condition what we are going to maintain.